we're going to work now a little bit more into straight looking at angle relationships. And as we look into the angle relationships, one of the first things we're going to do is kind of take a step back a little bit from the proof stuff for like today-wise, and kind of go back to the algebra for a second. It helps out two things. One, you guys are still having a heck of a time trying to solve algebra. Believe me. We're going to talk about that here in a minute. And two, it's going to re-emphasize a lot of the material that we've been working with via progression to help us as we get back to proof. Now, what I want you guys to have out while we're doing some basic notes here, nothing too crazy. Like I said, there's not a lot of, most of this stuff is kind of, we've already talked about. But what I want to do is I want to re-emphasize some of the things that were on your progression sheet that will show up here. And I need to make sure that you guys have the right information. Because when I was looking at your stuff last night, as I was grading through all the things, a lot of the things that I'm seeing is that, well, you are really making stuff up. You can't tell the difference between a segment and an angle. There's a lot of really, really silly problems that you're messing with. And it all can stem, you can fix everything pretty much by this and understanding what it means to use substitution, okay? That's really what everything stems out of. Everything else is I'm not trying to get you guys to memorize anything. I don't need you to memorize any of this stuff. I'm not trying to get you guys to really overdo like a real high complexity of things. But the problem is that there's not a lot of your side effort on it, okay? I know they're hard, but they are, okay? This is totally, and completely new to you guys as far as ways of thinking, ways of working, doing math, because it's not like what you would normally consider math. It's not solve for x, you know, that kind of things. What happens here is, though, it's the idea that you have to understand how do you manipulate a problem? How do you work a problem to come up with some solution? How do you use that information to deal with something else? And that's one of the big picture things in high school math is as you progress through your classes, which remember you have to have 3 years of math to graduate, this usually is the middle one. And as you progress through your stuff, you're going to be asked to independently think more and more. Students struggle with independence. You want to be spoon-fed and told what to do and when. As we get further along, we do less of that. You have to develop your own thought process. And that's what a lot of you guys have problems with because it's new. It's okay to try. It's okay to make mistakes. But randomly writing things down that make no difference or make no sense whatsoever to a problem, just by saying, oh, I'm just going to fill in the blanks just to make it look like I tried to do my homework or something along those lines, that doesn't work, guys. I see right through it. It's not my first day. Okay? Just so you guys know that. So when I go back and I look at, let's see, we had 10 reason bank things from Friday into Monday, a fill in the blank proof, so basically 2 questions. Monday night into Tuesday night I had 4. And you count all that up, and I think it was well over 60% of the work was neither attempted or less than half of it was even tried. So right off of that, when you don't put the effort into just trying, I get it, it's hard, it's tough, it's whatever. It's difficult. But the idea that you don't try means you'll never succeed. Does that make sense? It's okay to try, but it's also, you have to remember that when it gets really close to those quizzes and things, yeah, flex is great, but the problem is that there's only so many passes to go around, and there's so many people that come in. I have 106 or 107 geometry students total, as well as another almost 68 Algebra 2 students. So I'm looking at every day 170 some odd kids, which a good chunk of them want to come in, and I have to hold off on passes. I can't let 17 people from first hour, and then 10 people from the second hour go, and then nobody else goes. I kind of have to ration them throughout the day. That's kind of a problem sometimes, because I know some of you guys have other stuff to go to. You have other things like that. But you can't wait till the day before. And I've said that before, you can't. You got questions, you swing by in the morning, there's usually nobody around. Okay? I've said this before, but a lot of times, remember, I have to go pick up my kids from school after here. They can't get off the bus by themselves. You know, they can't go home by themselves. They're a little too young for that. So I usually can't stick around. You know, that's the downfall for that. Well, at least for a few years. But you guys be gone by the time my kids can stay home by themselves. Goodness will be gone. So just remember, guys, it's the idea that you try. It's the idea that you're following what we're doing in class, taking notes, staying off the Chromebooks when we're not using them, staying off your phones when we're not doing anything, okay? I know there's a time and a place when, you know, why I let you guys work, and I don't care if you're listening to music, because I usually have, you hear it when you walk in, there's always something going on. But there's a time and a place. And when we're here, I want you guys to be with what we're trying to do, okay? You guys have to make an effort as to what we're going to do to succeed. We can't just slough off this stuff and just kind of push it by the wayside. So we'll talk about the quizzes here in about 10, 15 minutes. That's about all I have to start with stuff for today, because I just want to, bless you, I just want to go through some basic notes, make sure you're on the right page with some of the few setups that are on the progression sheets, because this is where a lot of stuff stemmed from, to make sure that we'll be ready to go for next week. Because, well, I think we're going to test through most of the stuff midweek next week, Wednesday, Thursday, or somewhere around there. So, angle pair relationships. We know this. We've said this. If you look at your progression sheet, if you look on your progression right now, it says something about right angles. Somewhere along the lines it said that you should say that right angles are congruent. They're congruent to each other. Because what does every single right angle measure? 90 degrees. If two things measure the same thing, they're equal. Things that are equal measure are congruent. Yes, sir?
What's a third?
Oh, thank you. Theorem.
Oh, okay.
I abbreviate everything. I'm sorry, I didn't realize it didn't. It just means it's a theorem. To be honest with you, I don't really care if you guys know that it's called a theorem, a postulate, a definition, anything along those lines. The main thing is, what do you know about all right angles?
They're congruent.
Yeah, and you're right there. And so you know two things. So you know more than he does. But now you know two things, right?
Yeah.
So you're equal.
Okay.
I don't know. It's not a smile. Things make sense in my brain sometimes, and they don't usually come out right. So I apologize.
What's the definition of a theorem?
A theorem is it's an accepted, I don't want to say, you know how they have hypotheses in science?
Is it like a theory that's proven right?
Yeah.
Okay.
It's not a law. It's not like a scientific law. It's along that line.
Okay.
So we know that all right angles are congruent. We've said this in a progression sheet. We would say, hey, if this is a right angle, hey, if this is a right angle, we know those two are equal because they're both 90 degrees. Things that have equal measure are congruent. We've said that. The other thing that we've done, what we haven't done, is something about what's called congruent supplements. And we're also going to have something on here called congruent complements. Let me write this out on a separate sheet here. We have congruent supplements. I don't want to do that. Versus congruent complements. So we have congruent supplementary angles, and then we have congruent complementary angles. Here's what happens. First thing we have to remember is, what is a supplementary angle? How many of them? Two, good. Supplementary angles are two angles that add up to equal 180 degrees. What are complementary?
Two angles that add up to equal 90.
Perfect. So we know that these are going to be angle plus angle equals 180, and this is angle plus angle equals 90. That's what we had in our progression sheets. We talked about that as far as what would you say. But what this theorem states is that if two angles are supplementary to the same angle, those angles have to be the same. It's kind of like using a proof using the substitution step. It's actually very, very easy to see if I draw a diagram. If I just draw that, those are just two lines that intersect, do you agree? Now, when two lines intersect, you get how many angles? 4. How many of them are, normally, how many different angle measures are there? 2 of them. When is there just one angle measure? Say it. You got it. When it's yes.
Okay.
When they're perpendicular.
Yes,
If the two lines intersect, they're perpendicular. How many different angle measures are there? 1. It's just they're all 90. You had it. You went like this. I'm like, yeah, you're right. Okay. So if you think about this, if I back this part out, just for right now, and say that this is 130 degrees, what does that angle have to be? 50. It has to be 50 because they are supplementary. Now, if I go the other direction, and I hide this side, oops, what does that angle have to be? 50. So these two angles then are both supplementary to the same angle because they both have to add up to 180. Therefore, these two angles have to be equal. Doesn't that also look like vertical angles? It looks like vertical angles, especially when you are at two lines intersecting. But do supplementary angles have to be not what's the term I'm looking for? Rating? No, coterminal, not coterminal. No, that's lines. Oh, no, where they have the same vertex. No. Why am I drawing a blank?
I had to
Two angles there that share the same common vertex and the side, no internal points there. Yes. Thank you. Thank you. I don't know why I completely forgot what that was called. I'm sorry. But when you have adjacent angles, they're the ones that are right next to each other. But remember, supplementary angles don't have to be adjacent. They could be on two different, as long as the two angles add up to 180, they're supplementary. Linear pair are the ones that are adjacent supplementaries. Those are more specific. Okay? So supplementary angles, basically this theorem says if two angles are supplementary to the same angle, the two angles are congruent. What it might look like in terms of a proof then, you might see this. If I say angle 1 plus angle 2 are supplementary, obviously that's what it would look like. And then if I say angles 3 and angle 2 are also supplementary, what has to happen with 1 and 3? They have to be equal. Now, what we've done in the past is that we would say that these two have to be equal because they're equal to the same thing. What you can do with this congruent supplement thing is just switch them out right away. It's one of those little shortcuts that'll happen. I don't believe we do any proof with congruent supplements. I really don't, because we can always do substitution with it. We don't have to do that big step. All right. So that's why I don't worry about throwing that as a progression. I don't worry about that as a progression whatsoever. But what I do want to look at is just in case it comes up algebraically, which it will. Okay. What do you think changes with complementary then? It's just 90 degrees then? It's the same thing, guys. It's the exact same thing. If two angles are complementary to the same angle, they have to be congruent. So, I don't know why I didn't write this out. So basically, here's your idea. If two angles are supplementary to same angle, then the two angles are congruent. That's basically what we call congruent supplements. Okay? Two angles are congruent, or two angles are supplementary to the same. They have to be congruent to each other. All right. Non-adjacent supplementary angles on the back wall. Those 120-degree angles, aren't they the same? Aren't they both supplementary to the same angle?
Yep.
So what do you know about 120 and 120? Don't say it's 240.
They're congruent.
That's all it is. That's all that means. It looks the exact same. It works the same way if you don't have them adjacent to one another. What's that? Yeah, we do this a lot of times. There's, I'll show you an example here in a second of what that looks like written out. It's not so much the, you know what? Let me just go get that now. Yes.
Yes. That deserves some clap.
You have no idea how good that feels because I never make that work. It always screws up. I always screw that up.
You think you can do it on a small board?
No, because this has got a little tray.
Yeah, I know, that's the thing.
Yeah, I know better not to do it on the smart board. So, what you were asking was, what will that look like? It's going to look like this. It'll look like this. Oops, sorry, that will nice. Let's say I wanted to draw what this looks like. I have angles 1 and 2 are complementary, angles 3 and 4 are complementary, and 1 and 3 are vertical. We've done a little bit of like this, yeah. We've done a lot of draw diagrams using definitions, trying to figure out what the diagram is going to look like. So yeah, and like you were saying, what is that going to, problem like that's going to look like? It's going to be worded in such a way that it's going to ask you to draw a picture a lot of times. It'll be like angle 1 is supplementary angle 2, angle 3 is supplementary angle 2. They're all non-adjacent. What does it look like? Okay. Well, let's see here. If 1 and 2 are complementary, what do they have to add up to equal? 90. So that means what I would do here is I would draw a right angle. Does it matter what I say 1 and 2 is equal to? Because I have one at 45, the other one at 45, and I have one at 89.9, the other one at 0.1? Or, yeah. I'll just do this. But I have to put this in. Okay? That tells me that it's correct. All right. Then it says that 3 and 4 are complementary, but 1 and 3 are vertical. So, we'll move this over. What I'm going to do then is I know that angles 1 and 3 have to be vertical to each other. Does that make sense where I'm going here?
Yep.
And then this has to be to 4 to do. That's what that will look like. There's probably other ways to do it, but that's the way I thought of. You could have flipped the 4 to the other side, I guess. Hey, do you know what those 3, if you think of it, you've got 3 rays there? See how we got the 3 rays? Hi! It's awful. This is how you graph things in 3 dimensions. This is your X, Y, and Z grid. You guys have all been dealing with stuff in 2-dimensional space when you graph. In algebra 3, in algebra 2, we actually talk about 3-dimensional space. So you can go out some value, up some value, and float something into space. So this just kind of looks like a 3-dimensional space. You don't have to worry about this now, but that's something you'll see in a year. What? 3-dimensional space, it's cool. It's what you live in. Hi! We missed you. Because you were worried that we were going to hide it on you.
Yeah, because there's something valuable.
Well, all right, here's the other one. We already know this. We know about linear pairs. If you look on your progression sheet, I believe on your progression sheet it says something about linear pairs. It should. On your progression sheet, now again, you don't have progression sheet in front of you, put it in front of you so you can double check it. on your progression sheet, it should say something about if given linear pair. What does it say then to state after you have if given linear pair? No. What does it say? This page, what does it say?
The angle plus such linear.
Exactly. Where do you think I got that from? From this. As soon as you know that you have linear pair, what you usually do in terms of a proof is that you're going to wind up saying that these things are going to add up to equal 180 degrees. Well, the easiest way to do that is to use this definition. If two linear pairs form a linear, if two angles form a linear pair, then they have to be supplementary. That's what we utilized on our progression sheet before, because then after you know that you have supplementary, then we would say that the angle plus angle equals how much? 180.
180.
That's how that would work. You're given bits of information. What do you use that information with? Now, if I told you an algebra problem, and I said, hey, angle A and angle B are a linear pair. Angle A is 3x, and angle B is 2x. What do you do to solve for angle A and B? 70 equals 180. Exactly. Because you know that linear pair creates supplementary. You know that on here it says if they're supplementary, they add to equal 180. So we can utilize this same idea as these progression parts, because these are all your definitions, guys. This is how you solve all the problems in this chapter, because all the notes are here. This is an open note test. Okay? So I know this then, I would write 3x and 2x is 180. What's 3x and 2x?
5x.
5x. Now what?
Divided both sides by 5.
Did anybody ever show you guys how to do shortcut division? 5 goes into 1 how many times? Doesn't. 5 goes into 18 how many times?
3.
See that? How many are left over? 3 times 5 is 18.
3.
5 goes into 30 how many times?
Oh my goodness.
What did you just do? You know what I did? I did long division shorthand. Watch what happens. Here, I'll show you again. What I'm doing here is simplify a fraction. Okay. This is the exact same thing as doing this. 5 doesn't go into 1. 5 goes into 18 3 times. Subtract it out. 3. Drop the 0. You get this.
I don't even know how to do that.
Well, you really should.
You don't know how to do that?
What I did here was this is old-fashioned long division. This is just a shortcut. 5 goes into 18 how many times?
3.
How many times, Nigel? How many?
2.
Mr. Bobo, would you do me a favor?
Hit him.
How many are left over? 3. 5 goes into 30 how many times?
6.
Stop saying 2, bro.
So that's just shortcut division. Hey, on another note, guess what you're going to have to do again next year in Algebra 2?
What?
Long division.
Wow.
No. You do long division with polynomials. This is a way to factor. It's very, very easy. I'm not going to show you now, but I'm just saying it is very easy to do.
Yeah, I know. I just want to.
Excuse the interruption, please. Staff, if you're available during your lunch period, please feel free to come to the forum for a debrief from earlier this week. Thank you.
I'm gonna debrief. Is it 4 or 4?
Oh, is it the like mechanical malfunctions?
It's probably like,
Hey, we have this on our sheet. For what?
Was it the malfunction?
What's that?
Was it the malfunction there?
Yeah. No, this, I know you guys don't believe half this, well, 15% of the stuff I say, but this is the 85.
Okay.
They had, when they did that, it's actually more part of the intruder drill portion than the malfunction stuff. What happened with the malfunction was that they were testing something down at the Ed Center, part of like it's Fire Prevention Week, like nationwide. I know that my wife's school, she was saying that they had an intruder drill. My son's school had a fire drill the other day. It's a lot of those little things are going through the systems where everybody's testing systems. And they tested the system at the Ed Center. I think something didn't work correctly, and that's why it triggered the alarm systems here. So then when they had the alarm systems here, everything went to lockdown, and then certain doors weren't shutting and all that. I was sort of finding out there's protocol parts that were messed up. Yes, sir.
Or maybe it was a Mandela effect.
Oh no.
You guys and your silly Mandela thing.
Universe, and there's just fire alarms.
If you guys worried so much about the minutia that you talk about as you did like actually doing your homework, you guys would be straight A students.
Dang. Until Shane Dawson makes an algebra or geometry video, I will. No, never mind. Just, no.
Still who?
Shane Dawson is a YouTuber.
Who?
Shane Dawson.
You know
Who?
Will Graham?
He talks about
yeah,
the
he's close with it.
oh great.
He talks about the Mandela effect.
Ew.
Oh,
That's real.
Hey, that's awesome. Remember, guys, this is one of the things that we have. This is something that we talked about. We put this on a progression sheet. We have yet to have to actually utilize it yet into a proof, because this is something that is not going to be given to you. This is one of those things that you're going to be able to use algebraically a ton, or when you're looking at a diagram, it's something that you can infer from a diagram. Whenever you have two lines that intersect and you have what are called opposite rays, that's a hyperbola. When you have opposite rays, they make lines. The angles that are opposite one another are always going to be congruent. And we've talked about this many, many times about how it works itself around because of supplements and all that other kind of junk. Now, what we've done is we've marked this in our diagram, and I believe I think on the progression sheet that I put on there, yes I did. Look for vertical angles. The reason that I asked you guys to put that in your square, look for vertical angles, was so that when you're working with the diagram, you can identify them. Okay? We haven't done this yet within a proof, but if you have your, remember the little pack that I gave you guys on Tuesday where I had the 6 problems? Will you take that out real quick? I want to look at the 7th problem. And I want to show you how this works with a vertical angle setup into a scenario like that. Can I have this one over?
11 o'clock.
Wait, who's that?
Perfect. Got time.
Someone. We're like Haiti. We're in Haiti.
Wait, Tori, what are you talking about?
Does it say that? 1, 2, 3, 4?
Not sure.
Yes.
Which one?
Is that the right diagram?
Yes.
Okay,
Number
thank you.
7?
Yes.
Okay.
And then it says you're given, as in angle 2 is congruent to angle 3.
Yeah.
Okay. And it wants you to prove angle 1 is congruent to angle 4. So here's what happens when you are starting to work more with diagrams. Notice how they're only giving you one bit of information. They told me that angles 2 and 3 are congruent to one another. So if I'm looking at that given statement, what should I automatically do to my diagram?
Mark it.
Mark it, very good. I'll put in my tick marks for 2 and 3. But then, knowing that I have now vertical angles, what can I say about 1 and 2? They're equal. Well, how many tick marks does angle 1 have? Or, excuse me, angle 2 have? So how many does 1 get?
2, 1.
Whoa, 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 whoa. Let's back up here. Angles 2 and 3 are congruent, correct? I gave them both a singular tick mark. You just said that angles 1 and 2 have to be congruent because they're vertical, so how many tick marks does angle 1 get? 1. Same deal with 4, how many does it get? 1. Just by walking through that, didn't I just show that 1 and 4 are congruent? Now here's how you would write that down. Bless you.
Mr. Murphy,
Yeah.
can I go to the bathroom?
Yeah. We know that. Now, the first thing after I wrote that down is I marked on my diagram that angles 1 and 2 are congruent. Why are angles 1 and 2 congruent to each other?
Because they're vertical.
So here's how you write your reason. Vertical angles. Perfect. So I got it right. Okay. Vertical, yeah, just like a therm is a theorem. Therm.
It would be so confused.
I tried. So, vert angles congruent. Okay, so I got it right. Now, what do I know about, if I look at this then, I have 2 here, 2 there.
So 3 must equal 1.
3 and 1 are both congruent because I can take 1 in for the other using angles 1 and angle 3 are not congruent. Substitution. Why is angle 3 congruent to angle 4?
I don't know.
Because they're vertical. And then again, why can I replace the 3's? Substitution. Look how my numbers are written out though. 1, 3, 3, 4. So what happens when it's patterned like that? What do we use? We don't use substitution. We use
Addition.
Is it
transitive property. This one's transitive. Transitive? No.
He's just kidding.
Not all of it.
Remember, A equals B, B equals C, A equals C. When it's on a diagonal like that, when it's on a diagonal, you guys remember what slopes are? No.
Just kidding.
When it, even she was looking at rolling her eyes at you. Come on. Tori was just like,
Okay, continue.
yes, you did. Maybe you didn't. I don't know.
Just continue.
It just sounds fun. It's got a positive slope. Whenever you have the same thing repeated that has a positive slope like that between each other, that's the only time you use transitive. Is it wrong that it's substitute if you say substitution? No, but is it more right to say transitive?
Yeah. Should actually.
Shouldn't be. That's good. You remembered it. And that's how this would work. That's how problems like this will show up when you have vertical angles. Vertical angles are very easy to work with. It's just a matter of identifying them out of a diagram. That's the big push for a lot of this, guys. What information can you take from a given situation? Then what can you say about it? That's what we're trying to teach you guys, okay? Homework's already on the calendar. I only have like a couple of problems as far as the, where is it here? It's just pretty much algebra problems. You guys should be able to fly right through it. It's in the book. It's on page 128. I think it's like 16 of them. They're really, really fast. Okay?
I'm so good at the